Hello everyone. So in the last class we had spoken about the percentage enol content in different type of compounds in the tautomerism series. Now in today's class we'll be talking about racemization due to enolization. This is mostly our last class on the tautomerism. So first of all, what does racemization means? Racemization means when a product is mixture of the same molecule with different optical activity. So basically the molecular formula is same but the optical activity is different. That means if one compound is R, another compound is S, compound is same, its optical activity is different, is opposite to each other, the combination of both forms the racemic mixture. So this is what exactly happens when we do the enolization. So what exactly happens in enolization? Whenever you take an aldehyde or ketone and you place it in the acidic or basic medium, so aldehyde or ketone will tend to enolize. So basically it will get converted into its respective enol. And if let's suppose the enolizable hydrogen which is participating in enolization process is at the chiral carbon, that means the hydrogen on the chiral carbon is involved in the enolization, then the product what you get, or after the interconversion of enol to ketone and ketone to enol, whatever you get is an optically inactive racemic mixture. That means if initially your aldehyde or ketone had an optically active carbon with enolizable hydrogen, then after enolization and then after enolization converting into enol and then converting back into aldehyde or ketone, this whole process of a to and fro conversion from keto to enol and enol to keto, what you get in result is a racemic mixture. Now what do I mean? Let's see, let's understand it over here. So look at this molecule. What I have taken it as an example over here. So if you look at this is the keto group present over here, and I have the carbon which has enolizable hydrogen, right? So now what will happen when the enolization process will take place? This hydrogen will shift over here and this double bond will shift over here. This is what exactly happens when the enolization takes place, correct? So now when this will happen, how many enolizable hydrogens I have? One. On enolization, this hydrogen will come over here, double bond will shift between this carbon and this carbon. So this was, if you look at this carbon, there are four different groups present over here, phenyl, hydrogen, methyl, and this other group. So basically this is an optically active carbon and it is S configured. This is optically pure compound. On enolization, it will get converted into this in the acidic or basic medium. This is the enol we will get. There is a double bond over here and OH over here. Again, this enol will get converted into its keto back in the acidic or basic medium. But when the again conversion into keto will take place, at that time the hydrogen, because this is the planar molecule right now, the hydrogen can come and attach into any direction. So depending upon from which direction the hydrogen is coming and attaching, you may get the molecule S configured or R configured. So basically once the compound has got converted into enol, from enol converting back to aldehyde or ketone is a process where racemization will take place. How will it take place? It will take place in such a way that H can go and attach anywhere on the planar carbon. This is your planar carbon. This hydrogen will come out again and will attach on this carbon. Now it can attack from the back side or can be attacked from the front side. Now from where it is attacking, depending upon that, the configuration of the molecule would be. So now here it can be hydrogen here, methyl down, or I have done a small mistake over here. Here it can be your methyl here and hydrogen here. So either way the positioning of hydrogen and methyl can be, depending upon the position, the S and R configuration will be, and both will form in the equal proportion. And hence we say that after enolization, when enol get converted into aldehyde or ketone back, the racemization take place. So initially if your aldehyde or ketone was optically pure, it will not remain optically pure for a longer time. So your resultant mixture or compound will become optically inactive racemic mixture. Okay, so enolization causes racemization. This is what you have to understand. But the important thing is, it will happen, racemization will happen only if your hydrogen, the enolizable hydrogen, is present on the chiral carbon. If chiral carbon is present somewhere else in the chain, and if we are not taking the hydrogen from there for enolization, then racemization will not take place. What do I mean? Let's understand it through the examples. Now let's suppose I have this as a compound. So these are the compounds which I have taken. We have to understand where the racemic mixture will form, where it will not form. So look at this carbon. This is your keto group and this is your chiral carbon. So when the enolization will take place, the hydrogen will go from here. Okay, and double bond will shift over here. So this is how your enol will be formed, and this enol will get converted into keto back. Once it will get converted into keto back, this will give you the racemic mixture. So this molecule is capable of giving you racemic mixture. Why? Because your hydrogen is coming out from the chiral carbon. Now look at the next compound. In this compound, this is my keto group. Here is this CH2, this CH2. So now enolizable hydrogens are 4. 2 from here and 2 from here. But understand this thing, that none of these carbons are chiral. Whereas look at this carbon, this is chiral, but we are not taking our hydrogen from here. So enolizable hydrogens are in this carbon and in this carbon. So there will be no racemization takes place. Because even if the hydrogen goes from here or hydrogen goes from here, the configuration of the molecule will not change, because these are not optically active carbon. Though we have an optically active carbon over here, but there is no enolization taking place over here. We are not touching the hydrogen of it. Hence, whatever the configuration of this chiral carbon is, that will remain as it is over here. So no racemization here, no racemization. I hope you would have understood. What I'm trying to tell you is the carbon which have enolizable hydrogen, if that carbon is optically active, then only the racemization takes place. If the chiral carbon is somewhere else in the whole chain, then racemization will not take place. Okay, now look at this case. In this case, you have keto group over here, enolizable hydrogens here, and no enolizable hydrogen here. Even though this is a chiral carbon, no enolizable hydrogen. So no racemization will take place. Hydrogen will go from here. It will form PHC, Me, Et, C double bond, COH and H2. So this will be forming, and this carbon doesn't have the enolizable hydrogen, so it will not, even though this is chiral, it will not be involved in the enolization process. Hence no racemization, no racemization. Exactly same way, look at this case. We have the keto group over here, no enolizable hydrogen here, and this is also not enolizable hydrogen, sorry, but it has a distant hydrogen over here. Look at this. So here, this is the enolizable hydrogen. It is at the it is in the distance relation. I told you what is the distant relation. This hydrogen can get involved in the enolization process, and there is a extended conjugation over here. So this is what we expect. This is my chiral carbon. It has enolizable hydrogen. This hydrogen, through the resonance process or through conjugation, will come over here, and the pi bond shift will happen. So the product will be PHCME, double bond CH, single bond CH, double bond COH, CME3. This is what will be the product, and this will again get back to the keto form after once it is formed enol. Then again in the basic medium, it will get converted into its respective keto. So when it will get converted into its respective keto, the hydrogen will come back at this position from here. So hydrogen will come back at this position. When this hydrogen will come back at this position, at that time hydrogen can come from front or can come from back, because this is planar right now, and this is capable of doing racemization. So racemization will happen. So this will give you racemic mixture. Okay, this is how you have to judge whether the racemic mixture will form in the respective compound or not. Now look at this. These are the questions. I have given you OH minus conditions. You have to just tell me whether racemization will take place or not. Think about it, take your time, and then solve it, and then I'll discuss. So look in this case, first case. What is happening in first case? In first case, first of all, figure out whether we have the enolizable hydrogens. This is my keto group. This is my carbon. This is another carbon. Here also we have 2 enolizable hydrogens. Here I have 1 enolizable hydrogen. So yes, we have hydrogens which will participate in the enolization. Now look at this carbon. In this carbon we have 4 different groups. So this is your optically active carbon. So this optically active carbon has an enolizable hydrogen. When this will participate in enolization, hydrogen will come over here and pi bond will shift over here. So the molecule will be like this. Look at it carefully. This will be methyl over here, OH. This is how the molecule will be. and this will again get back to its keto form in the basic medium. When this will get back to its keto form, or you can say this will get converted back into this. So when this will get converted into this, there are two type of products possible. One is the methyl is in the front, and hydrogen is at back. Other possibility is, both the products will form. Hydrogen is at front and methyl is at back. In both the cases, the configuration would be different, and hence the racemization will take place. So two different products will be forming, hence the compound will be racemic mixture. Okay, so racemization is possible in this case. Now look at the next compound. In next compound, this is your keto group. This is the carbon which is optically active and has enolizable hydrogen. In this case, no enolizable hydrogen, hence even though it's optically active, its optical configuration is not gonna change. Now the product will be in such a way, after enolization, again getting back into the ketone form, the product form will be, I'm not writing the product, I will just write the configuration. So this S can get converted into R also and can get converted into S also. This S will remain as it is. This will be S and S all the time. So basically two products will be forming. One will with the configuration of R and S with two optically active carbons, and other will be SS. So this is optically active mixture. This is not optically inactive mixture. Why? Because for optically inactive mixture or racemization, we require completely opposite configuration. Here the configuration is not opposite. These are distereomers. For optically, for completely opposite configuration, it had to be RS and the other should have been SR. Then it would be optically inactive. But this is optically active compound. Hence, we will say this, if this is the product forming this and this, then the distereomers are present. And if the distereomers are present, it will be optically active. So no racemization is taking place here, even though this compound has optically active carbons and your hydrogen, enolizable hydrogen, is on the optically active carbon. So you have to be very smart and carefully, you have to be very watchful that how the reaction is taking place and what would be the product. Just do not go by one simple rule that the chiral carbon is there and it has enolizable hydrogen, hence the racemic mixture will be formed. No, you have to be careful. Look at the another carbon also. If that is also optically active and is not participating in the enolization, then its configuration is going to remain fixed and it will not change, and in that case it will give you distereomers. Look at the seventh compound. In case of seventh compound, what will happen? This is the carbon which will be involved in enolization, and this is the carbon. So here this is optically active, and this carbon is also optically active. So two carbons are optically active, and hence you will get distereomers. For this carbon, the configuration will change. It will be R and S. And for this, whatever the configuration is, that will remain fixed configuration. Assume if it is R, it will remain R. If it is S, it will remain S. So basically you are again gonna get the distereomers. So again, it's no racemization is taking place. No racemization. These are the important questions. You get such questions in the advanced papers. Next topic we'll talk about is D-exchange. D-exchange means deuterium exchange with hydrogen. So basically what's going to happen here is, we know that we have enolizable hydrogens in the keto form, and now if we keep that keto or aldehyde in the presence of OD minus D2O, basically in the basic medium, but when you talk about the basic medium, it is not OH minus, it is OD minus, and even the water you are taking is a heavy water. In that case, what will happen? All enolizable hydrogens will get replaced by deuterium. That's all. And the process which takes place, or the mechanism which it follows, is the enolization mechanism through which it actually replaces the hydrogens with deuterium. Let's see. We have RCH2COR. We have two enolizable hydrogens over here. And in the presence of OD minus with D2O, what we will see is two hydrogens have been replaced by two deuteriums. How this process has taken place, as I mentioned, it takes place through enolization. How? Let's understand. So first of all, OD minus will come into the picture, and in the presence of the basic medium, what exactly is going to happen? This OD minus will pull away the hydrogen from this carbon where the enolizable hydrogens are, okay, and this carbon will become carboanion, and this carbanion will try to form a pi bond over here. In that process, this carbonyl group will break. This will become CH double bond C. You remember this? We have done this basic medium mechanism earlier also, where I had explained to you how enolization takes place in basic medium. So exactly same procedure it is following. right? So now here this has become CH double bond CO minus. Now when we have got CO minus here, from heavy water it will take D will attack over here, and this will become OD. Now this we have got into the enol form, but in enol it is not OH, it is OD. This will again get back to its respective keto. It will get back to its respective keto by losing this D. This O will try to get back to its normal form by forming a pi bond, and this pi bond will also break, and this D will eventually shift over here. So this is how it will form. You will get a keto back here and it will become CHD. Now again this is a keto. It has one enolizable hydrogen over here. Again OD minus will attack on it. Again the same procedure will take place, and this will get converted into this form first, RCD double bond COD R. It will get back into this, and then again this will follow the same process, that OD will give its bond back, this will form back again, and D will come over here. So this is the molecule what you will get. So exactly the way how mechanism takes place in the basic medium, same procedure is happening twice, and two enolizable hydrogens are getting replaced by deuterium, and that deuterium is coming out from the water. Okay, this is how exactly the reaction takes place. In the presence of excess OD minus and G2O, all hydrogens, enolizable hydrogens, get replaced by deuterium. This is very important. You need to understand this, and this is very important because they ask you in many reactions in advanced paper. This is a very important implementation of this concept. Now I have given some questions over here, and you have to figure out what will be the product formed when these compounds have been kept in OD minus D2O after enolization. Once it will form enol, and then it will get converted into keto. How its keto will look like, this you have to tell me. Try it out on your own, and then I will tell you the answers of these. I hope you have done all of it, and let's discuss the answers now. In every place here there will be deuterium, so it will be CD3, C double bond O, CD3. This will be the product formed here. These are the places where the replaceable hydrogens are. So it will form CH3, CD2, C double bond O, and CD3. Here again, here is the replaceable hydrogen, so it will form PH, C double bond O, CD3. Here again you have here replaceable hydrogens and one here, so it will form D over here, C double bond O, and CD3. And in this case, here are your replaceable hydrogens, so it will form double bond O, D2 here, and D2 here. This is how exactly you will write the answers when the reaction is taking place in the presence of OD minus and D2O. Right? Now let's talk about tautomerism in phenol, and this is the last topic of the day. So tautomerism in phenol. Now just think, when we talk about phenol, what is phenol? This is phenol. Isn't this enol actually? This is OH with the carbon having the double bond. So this is what exactly the enol structure is. And what we have seen is that the keto forms are generally more stable than the enol forms. Then why the phenol is actually an enol and it is being sustained in this form? Why doesn't we see its keto form so often? The reason behind this is when this phenol is present in the enol form, in that case you see the ring over here, this is the benzene ring, and this has alternate double bonds. This is an aromatic structure, and aromaticity is very, very important factor for its stability. We have also learned it in GOC that aromaticity comes first in the order of stability. If you have to look out for any effect, any electronic effect, if any compound is aromatic, that is basically the God thing. Aromatic means aromaticity fails all other electronic effects. If there is an aromaticity in the molecule, that molecule is gonna be the most stable one. So because in the enol form, here is the benzene forming, which is an aromatic compound. That is why it is very, very stable, and hence phenol exists in the 100% proportion, and its keto does not exist. Or even if it gets converted into its keto, it does not remain there in the solution for a longer time. So it does not exist in the keto form, you can say it that way, or keto form is not sustainable because it is very, very less stable as compared to its aromatic ring structure. How does exactly the tautomerism takes place in phenol? Let's understand. So this is OH minus. The process is exactly same. We are doing it in the basic medium. So what will happen? This oxygen will try to form a pi bond over here, and the pi bond present over here will break, and H will basically go to the carbon over here. So this is how exactly it is happening. The H plus will be taken away by this OH minus. So we will get O minus over here. This O minus will try to form a pi bond, and this pi bond will break. So here we will form a keto thing, right? And then this negatively charged carbon will get into the resonance now, and the negative charge will come over here, and then negative charge will come over here. So basically negative charge can travel into 3 different positions: ortho, para and ortho, and that's how the keto will be. And then when it will be treated with water, this negatively charged carbon will take hydrogen from here and will stabilize itself. So if the negative charge is here, then the hydrogen will come and get attached over here, and this is what you will get. This is your keto form of the phenol. If the negative charge is here, then hydrogen will come and attach at this position, and this is what you'll get in the terms of keto. And if the negative charge is here, then hydrogen will come and attach over here, and this is what you're gonna get. So basically 3 different forms of keto you will get for phenol. And all of these forms are lesser stable than this form. Why? Because the ring what you're getting has conjugation, is capable of doing resonance, but definitely not the closed conjugation, and definitely it is not following the aromatic structure. So no aromaticity, it is a non-aromatic compound. And non-aromatic compounds are lesser stable than your aromatic ones. That is why the keto forms of it are quite less stable, and hence phenol exists in the form of enol, basically benzene with OH, rather than in its keto form. Now you have understood how the enolization process can take place in phenol. Try to form the keto forms of these benzene diols. Do it on your own, and then I'll show you the keto forms of these structures. Try it out. Give yourself good amount of time, and then let's see what all different keto forms can be formed for 3 different compounds, three different benzene diols over here, and which one is stable, whether the keto form of it is stable or enol form is stable. Now let's see the solution of it. I hope you would have tried it. So here assume, you can do it in 2 ways. Both the OH, you can enolize them together, or you can do it one by one. So assume this OH minus is taking away this hydrogen. So what you'll get is, so oxygen putting the electron density on this bond, and then this pi bond is breaking, and the negative charge is forming over here, and then water is giving hydrogen over here. This is one way. Okay, and then the other OH gets into the enolization process. Or you can do both of the reactions together. How together? Let's say this is my molecule, and there is a double bond, OH over here and OH over here. OH minus, 2 OH minuses are there taking away these hydrogens from here. This is O minus, this is also O minus. This O minus will push the electron density here, and this pi bond will break. Again, similarly, this O minus pushing the electron density here, and the pi bond is breaking here. So this can be like this. Double bond oxygen over here, double bond oxygen over here, negative charge over here, negative charge over here, and a pi bond is already here. And then water's hydrogen is fulfilling the valencies over here and making it this way, right? So it is like adjacent diketones what you're getting, which are highly unstable due to the lone pair repulsion. We have already seen that. So this does not exist in this way. So this exists as in this is not stable in this form. So this form is more stable. There are 2 reasons for instability. One is repulsion. Second is aromaticity is gone. So this form is not preferred. Look at another thing. Another thing also exactly same way it will happen. I have the molecule over here like this, OH and OH. And then assume this is how the bond structure is. Hydrogen will go from here. Hydrogen will go from here. There is O minus over here, O minus over here. This will try to form a bond over here. This oxygen will also try to form bond over here. This pi bond will break, and this pi bond will also break. So I'm just writing it in a little clumsier manner earlier. Let me just write it neatly again. So this is, assume this is how the molecule structure is. So it'll be OH at this side and OH here. So hydrogen gone from here, hydrogen gone from here. So this will be O minus and O minus. So this will be valency will be pushed over here, and this valency will also be pushed over here. This bond will break like this, and this bond will also break like this. So it will be double bond O, okay, negative charge over here, then double bond O and negative charge over here, and this pi bond will remain as it is. So water's hydrogen will come after treatment with hydrogen. These negative charge will get fulfilled by hydrogen, and this is how your ketone will look like. This is your keto form. Again, it is less stable. Why? Because aromaticity of the molecule is broken. no aromaticity, whereas in the earlier molecule there was aromaticity, and aromaticity itself is a big factor for the stability. So in all the cases, no matter you talk about this one or you talk about this one or you talk about this one, in all the cases aromaticity would be the factor which will be the driving force for these molecules to exist, and these molecules not to be existing in the keto form for these benzene diols. In this case also, I think I have missed a pi bond over here. Here should be a pi bond. So these are the diol. This is the diol. Diol will look like this: pi, 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 OH and OH. Again, when this will participate in the enolization, we will get O minus and O minus over here. This O minus will be pushed over here. This will come over here. This O minus will push its density over here, and this pi bond will break. This will look like this. It is forming highly unstable species, by the way. Double bond O, negative here, and pi bond over here. And then hydrogens will come and fulfill the valency here. And this is what the keto will be formed. Again, it will be very less stable due to the broken aromaticity and no resonance in the ring. No resonance in the ring. The resonance is there from here to here, but no closed conjugation, no aromaticity. So it is relatively way less stable than its enol form. So enol form in case of benzene diols also is very stable as compared to their keto forms. So this is about tautomerization in phenol, and we are almost done with everything what we need to know for tautomerization. One small topic is left, that is ring chain tautomerism. But before I go to ring chain tautomerism, I would like to give you some questions to solve. You try out those on your own, and then we will discuss them in the next class. What is it? I am giving you some compounds. Find out their keto forms and tell me whether the keto will be stable or enol will be stable. Okay, so do this. This is one. Okay, another is this is another compound, and the third one is this is the compound. Now draw their keto structures and see the stability of the molecule. Now in the last class, I think I had told you that I'll discuss the solution of a question. That is, when I had given you this molecule CH3, C double bond O, CH2, CH3, I asked you to do the mechanism in basic and acidic medium and figure out the answer formed after enolization. So what enol will be formed when we'll treat it in the basic medium and when we will treat it in the acidic medium. So I'll tell you the answer first and then we'll show you the mechanism. So this will be your product, which will be the major product in case of your basic medium. If you are doing enolization in the basic medium, this will be your product formed. This will be a major product formed. And if you are doing the enolization in the acidic medium, this will be the major product formed. Now, how there are two different products forming for the same molecule, just by changing the medium, the product is changing. That you have to understand, and this is very, very, very important question. Okay, so let's go by the mechanism method and let's understand what has changed if you change the medium. So let's deal with the basic medium first. Okay, now in the basic medium, I have taken CH2, let me write it like this, CH2, C double bond O, CH, hydrogen and CH3. Why I have written hydrogens like this? Because these are the enolizable hydrogens. Now which hydrogen will be taken away, that we have to decide. Now we are treating it with OH minus. Now OH minus is a base which will basically abstract the proton, and then understand this thing, that abstraction of proton will be easiest if there is less steric hindrance. So if you look at this carbon, the steric hindrance is more over here, whereas if you look at this carbon, the steric hindrance is less. And for this OH minus to take out this hydrogen will be easier in this case. So it will always prefer taking hydrogen from this side. So if it will take hydrogen from this side, the product formed will be CH2 minus C double bond O, CH2 and CH3. This will be my anion formed, which will basically, this is my primary anion. Okay, and this will get converted into, it will shift the negative charge over here, and this will shift over here. So this will basically become CH2 double bond C, single bond O minus, and CH2, CH3. Now I'll treat it with water. So this is your slow step, by the way, and this is going to be your fast step, that is treatment with water. So if we'll treat it with water, this hydrogen will come over here and this will form CH2 double bond COH, CH2 and CH3. and OH minus will be back in the system. So this is the product what I'm getting. And why did I get this product? Because I chose to remove the hydrogen from here rather than removing it from here, because here the crowding is more, and base will always try to abstract the proton from the less hindered area. So this basic medium's OH minus actually caused the reaction in this way and took away the hydrogen from this carbon, though there were two places where the enolizable hydrogens were. One is this and one is this, but OH minus chose this carbon's hydrogen to be taken away. Now let's see in the acidic medium what happens. So let's write acidic medium. In case of acidic medium, I have, again, I'll write it as CH2 hydrogen, C double bond O, and then again CH hydrogen and CH3. Now understand one thing. So when we talk about the mechanism with H plus does not attack on hydrogens. It attacks on the oxygen, and this is your acid-base reaction. Acid-base reaction, and this is a very fast step. So when H plus comes over here, this basically gives you this COH plus and then CH. I'm just writing H over here because these are the enolizable hydrogens with what we'll be dealing. Now this oxygen has a pair of electron and one positive charge, which is not acceptable for this oxygen. And what this oxygen will do, this will forcefully try to form a pi bond. I think I have done a mistake. There is a double bond over here. So yeah, this oxygen will try to break the pi bond like this. When this will happen, this will get converted into CH2 hydrogen, COH, positive charge of oxygen will be gone, and the carbon will get a positive charge over here, and then CH, CH3. So this is the carbocation I'm getting. Now this is your fast step, and next step is going to be your slow step, and which is going to be the RDS, that is enolization step. Now here, what exactly is going to happen? So now this positively charged carbon can form either the pi bond here or can form the pi bond here by either the removal of this hydrogen or by the removal of this hydrogen. Now whichever way the carbon will form a pi bond, it has to see the alkene formed should be the stable alkene. Okay, the possibility is removal of this hydrogen and the pi bond formation over here. If that will happen, then it will form CH2 double bond COH, CH2, CH3. But if that doesn't happen, then the removal of this hydrogen will take place and the pi bond will form over here. And in that case, it will be CH3, COH, double bond CH, CH3. Look at this double bond. This is much more stable alkene because it is more alkylated, and that is what the funda of the stability of alkene is. So here the reaction will be driven in the direction where we are getting more stable alkene, and here we are getting the more stable alkene. So removal of hydrogen will take place from this position and the pi bond formation will happen over here because this is gonna give me a better stable alkene. So this is the product gonna be the major one rather than this one. So this will not form, this will form. So this is the difference in the acidic medium and the basic medium. In basic medium, the driving force of the reaction in a particular direction is that how easily accessible your H plus is, or how easily your OH minus can remove the H plus ion. So less sterically hindered carbon it will go to and will pull out hydrogen from there. Whereas in acidic medium, the driving force of reaction would be what kind of alkene are you getting? Which alkene is gonna be the stable alkene? The stable alkene will be formed, and that is how there can be difference in the product when the reaction is happening in the acidic medium or happening in the basic medium. So you have to be very, very careful while marking the answer, especially in such cases where the answer can differ if the medium is changing. So just do not go by random marking. Understand the mechanism and follow that mechanism when any such question has been asked where specific medium has been given. You have to check, you have to actually write the mechanism and figure out from where the hydrogen should be removed, because both type of answers will be available. This answer will also be available and the other answer will also be available, and you have to choose only one. So depending upon what medium has been given, you will choose the answer. Okay, so this is the solution of the question which I had given in the last class. Today also I have given you one question. Try it out on your own and then I will discuss in the next video. In the next video, last topic I'll be discussing, and that is ring chain tautomerism. That is gonna be our last topic for tautomerization. Here we are done with the tautomerization of mains level, advanced level, and every possible level. All the questions what can be asked are covered in these videos. Okay, so go through this, ask me doubts if you have any, and practice the questions so that you get thorough understanding of the tautomerism.